Hi everyone, today we will be doing project number 2. So the first thing we'll do is to get our file from Blackboard. So we will go to project number 2. Then we will download our final profile Tube Die DXF file. So you can see it here. I've already downloaded it previously, so it should be in my desktop. Let's do of it right now. Now we will open CompuPlast. So we go to Extrusion Experts, and we will pick, as you know, we will try to emulate a medical tubing die development using simulation and crossflow minimization. So we will do this by editing that DXF file in our profile die. So we will try to follow as these notes were taken in class, we'll try to follow the tutorial or try to set up our base die. So as in our tutorial, we first import our DXF file. So we place it in our desktop. So we have a true profile DXF. Once it's loaded, you can see that we can actually make it symmetrical and actually only need one half of it. We will edit that in a bit. So, but first we will try to save it. So for this one, we'll save it as our medical project 2. Click OK. And we'll close this. And that profile should appear here in our main menu in our profile shapes. So we will now open this and edit it. So as said, we will try to make it only 1/4 of the section, so it would be easier to analyze and basically optimize our die, because again, as said, it is symmetrical. So going back, going to full screen it to show you just the different things we're gonna look out for. So we'll look out for here X in our Y direction. So first, let's try to measure it with our angle and distance. So our total length should be 12. So as known and as stated in the tutorial, we will try to scale this down. So what we'll do is want to scale down so it is 10% of our original size. What we will do is go here to node, select all, then go to node and scale up. So instead of scaling up, which we'll also do later, for this one initially we'll want to scale down. So we want to scale down to 10% or minus 10% or 0.1. So scaling up. After that, we now want to delete that or make it 3/4 of that size. So you can do this in many numerous ways. One way would be to go to boundary and select our boundaries. So we can select all and maybe try to split it. You can split it so it's easier. So we'll try to select it. Select it, split it. As you can see, I'm trying to split it so it's easier. And maybe, yep, let's try to get this upper right corner section. So that should be good. Just set escape, and you can now try to delete this whole border. So let's go to border and delete. Yes, we want to delete this. As you can see, I did not delete some of these, so we'll try to delete these guys too. So we want to, as seen in the picture again, want to delete it maybe 1, 2, 3, 4, 5, 6, 7, 8, 9. So I want to delete it around here. So let's delete both of these. Delete. Select. Did not split that. So let's go split it. Split. Escape. Boundary. Delete. Yes. And so what you can do here now is basically You can also delete these guys, or circles. Do this by going again, delete. Yes. So to easily remove all our nodes, you can go to node. You can find delete redundant, and that will delete all our nodes quickly. So yes. Now we have our initial shape. So now we would want to close it. So to do this, you'd want to make a node in the middle here. So let's just select anywhere, spacebar, and 0, 0. So, oh, I accidentally made another node. So let's just delete this. Delete. Yes. And so we would want to connect it. So we'll do this by going to boundary. I'm going to add. So go to select this node, create one line. So we know that it's right when it turns into red. So go again, select it, just connecting it. So again, we have now connected it. You can now press escape to move it. So afterwards, we now want to basically divide this up into different sections. So it was recommended to maybe at least divide it into 6 sections. So let's just show it side by side. As you can see, there's 1, 2, 3, 4, 5, 6. And as you know, that inner tube, let's just resize it a bit. So as done in class, we would want to put it at 3 specific locations. So what you can do is go here, go to node, and we can add it either to add on edge or add on line. For now, we'll try to do add on edge. So again, we want to add it around, for this time, it's around going to be 0.45. So let's try that. So here, 0.45. As you can see in the upper lower right corner, we'd want to have our Y around 0.45. So let's find 0.45, 0.55, and the next one would be which is 1.5 away again. It's going to be around 0.3, as you can see. So around 0. That's pretty close enough to our Y, around 1.5. And we also want to do that for our lower section, or bottom one. So we go to 1.5. Now it's going to be in our X direction, as you can see. And the X 1.5. Put these 3 and 4.5. So as said beforehand, you can also do this by going to node, modify edge, and add on line. That would be, of course, more accurate. So you could maybe do it for the Y or 0. Let's try 0.5. That would add around the middle. So somewhere here. Oh, sorry, it would be here. Of course, we omitted that step to make it quicker. So nonetheless, we can now go to, we now need to basically add an inner boundary. So you can do this by going to boundary, add inner, and we simply follow it. So we connect, let's just deselect everything. Okay, now it's everything is deselected. So add inner, we go here to our 4.5, select this guy, connect it. Oh, I didn't select it. So select, my apologies, to boundary, add inner, select this node, and this node. Should create a line. Oh. This node, add inner. Node. Recenter it, add inner. here. There. Now add it. Just select it again. I'm going back for its reference. We connect this node to this node. Select it. So as I said, it turns blue to red. We know that it's working properly. So here, here, then select this guy into this guy. Afterwards, we do it here again. Like this guy, and this guy to this guy. Oh, you can press Control Z if we made mistakes. There. You can now press Escape, and it will save that. So, we have now completed the first step of our base of our die. So, just a quick recap of what our group did. We basically opened the file, our true profile file, which was a circle. And basically got 1/4 of it, or a section of it. Then we scaled it, as we also did, we scaled it to 10% of its optimal original size. Then afterwards, we divided it into 6 sections as shown in the right, or at least 5 sections. Then you can now save it and proceed to the next step.
As we left off, we saved it and exited it. We're going to go back to Medical Project 2. Copy. And paste it in the die cross section. We're going to keep it as an isotropic drawdown and keep it as 1. Which we can change later. This will give us our Z direction. We'll keep it as 0. We can also rename it to a transition zone or die exit, but we're just going to keep it the same for less confusion. Once we click OK, we'll be able to see the profile again. To show this is 0.6, we'll go to Angle, Laminar. We're going to scale it back up. We're going to select all and scale up. We're going to scale the ratio to 10 and then click OK for continue. Then we're going to go to Query and Angle and Distance again and do the sidewalls. And here we can see that all of them are properly defined. We can do a boundary split and select outer boundary straight lines. So they're boundary, select, and now we will try and split it. We're going to unselect all, boundary, select. We're going to get the sidewalls. Now we're going to go to type and we're going to change it to axis, and then hit OK. And that will be for both sides of the wall. For those, they want us to be wall fixed. So we select all of those and then go to boundary, go to type, and then keep it as wall and fixed. And those selected will be the inner boundaries. And we see that they are wall. So everything should be all set. We just press escape. Now we go under grid generation. There's another way you can do it. You go under common and grid generation, and then we click on automatic, and then press OK. Now we just save, and we can close it. As now the blue check, we should be good to go.
As we left off in a previous clip, we were using a different computer, so my file name is different, but we finished the die cross section, and now we just want to make the actual file and project data. So the original name was Medical Project 2, but I have it named as Project 2 Profile. That was when we scaled it back up and we only have a quarter of the cross section for the given die. So the radius is 6 millimeters. So we want to make copies of this for each section of the die. So we want one for the die exit, one for the transition plate, and then 2 for the balance plate. So this technically, since it's scaled back up, this is for the transition plate. So we'd rename it Project 2, go back, caps lock on, Project 2 Transition Zone, example. And we'll make a copy of that, paste, and we can copy it again, paste, copy it again, paste. Then we want to rename all these. So we can call this one Project 2 Die Exit example, and then rename this to Project 2 BT1, which is the first balance plate cross section example, and then this one is Project 2 BT2 example. So we need to we can optimize these after, but so this one is good as it is, but the die exit we want to be scaled back down. And the profile shapes already have the scaled down one, so we don't really need to mess with that for the project data file. So this is fine as it is. We can now set the Z value, the depth of it. So the die exit would be 0. Project 2, you go to edit and you set it to the value it should be. So 2.5 away, that's good. That should be fine. This one, BT1, that is located at 5 millimeters. So you edit that. So this should be 5, -5. Save. And then this one, we edit it again. That should be 15. We save that. So we also need to generate the grid for all of them, because when the file is copied, it doesn't save the grid. So we can start with this one. You can edit, and then just generate the grid. So this is what the die exit looks like right here, relative to the size of this cross section. So you can see it gets much smaller by the end as it goes through the entire die. So we just generate the grid, use automatic as before, save it, and then we do this for the other ones as well. So that was the transition zone. As you can see, it turns blue, which means it's ready to be imported into the project data. So we got to do that for these two as well, and like I said, for the die exit, we can just use the profile shape originally. So we added this. The Z value is -5. Generate the grid again, automatic, okay, save. It's the same steps for all three profiles. So now just the last one. Once it loads. Okay, that one's blue, so it's all set. Okay, we generate the grid again, as before, save it, close it. So now we can actually go into the project data section and make the actual file. So I already have one here because we tested it out before, but we can make a new one. Just call it medical die example, and then we can edit that with our 3 cross sections that are approved. So we import these. Oh, I already imported that one. So these are good. You can see it shows the Z values here, and we need to define the die exit, so that would be this under the profiles. So we have everything here, and you can see they're all the same shape. The die exit is 10 times smaller than the rest of them, but these 3 are the same profile. We should go to material now, and as instructed, we want to use polypropylene, 3.5 melt flow rate, Cario, however you pronounce that. Select that. Leave the temperature at 200 Celsius. We change the total mass flow rate to the value we were given in class. That's 0.0682 kilograms per hour. Here we go. And then the line speed is 5, and it will eventually round to 5.002 after we do the balancing. So now we need to balance each section. You just click on the profile, so use similarity, accept all, and you do that for each of them. And you can see these values become the same on both sides. So that's balanced now. Now we can go back to die definition and actually start. Or we would edit the grid if we were trying to optimize it, but first we want to see how optimal it is already. So we save and solve. And then we can look at the individual cross sections right here. So since the transition zone will stay the same, we're just going to look at one of these, and once we do optimize it, we just make a copy of that for both of them, because we want it to be the same profile throughout the entire balance section, so that the velocity stays the same, and then it's the die flow rate is constant throughout the entire thing. So we can edit either one of these. Like, I'll edit the top one. You can go to C cross section. Wait for it to load. And what we have here, we can see it's velocity is selected here, so this is high velocity and then lower velocity, and the blue is the lowest. So we can see that in this section the velocity isn't really the same as it is all around the other parts of this circular protrusion. So what we want to do is try to get this part to be red as well, in theory. And a better way to quantify it is looking at the percent area and percent flow rate in each section. So we have 6 domains as generated in the grid, and I would label them as domain 1, 2, 3, 4, 5, and 6, starting from here, because this one is the most significant difference. You can see That's about 8%, 24.8 minus 16.6. So that means those kind of need to be balanced so that you have a relatively even percent area and flow rate. You want them to be roughly equivalent, within at least 2%, ideally under 1%. So you can see there's a big difference here with this one. And then for the other ones, there's about a 1% difference here, 2% here, 2 here, 2 here, and about 1 here. So the real issue is fixing this, providing an even velocity all around the circle. And the only thing we want to change is the position of these nodes on the edge. We don't want to change the axis length at all, either axis. We don't want to change the dimensions of the circle here. We just want to move these nodes. We can make more nodes if we want, or take some away, but we just want to change the shape to whatever will make the velocity more even around the entire cross section. So to do that, we need to go back to the grid and mess with that. So we can close this. We gotta close the simulation, and we can open the file again. And it brings this back up, and since these are the same and we're going to copy the optimal one once we have it, you can edit either of them. So you can go to edit grid, continue, and we just want to change the position of each of these nodes if necessary. Just see what effect it will have. You can kind of start out using trial and error. So we'll show how to move the points to the most optimal position in a moment. But since I already did this and I saved some images in Excel, I will show what our progression looked like. Move this out of the way. So if you go here, you can see this is how I labeled each domain, D1 to D6. And this is the die exit, and this is what all the other profiles look like, the other 3. So I have images here along with little tables showing the percent area, percent flow rate of each section, each of the domains, and then the difference between them, which you want to be as low as possible. So you want this to be close to 0. As you can see for the first one, there's a significant difference between some of them. Almost 1%, 2%, 2%, almost 2, about 1. So this is for the default one, which is down here. And then design 1, I wanted to see what happened if I made it more narrow, which made it worse. I have this in each of these other tables for the other designs. I have a table called improvement, which shows how much it improved, how much the difference between flow rate and area got lower. And as you can see it by a negative value here, it got higher for this section. So that means it's worse. So that basically leads us to the conclusion that since if we want to make the velocity even around it, we want to expand the relative radius of this section. So I started out very slowly, just increasing it slightly each time, and eventually we got to something that was fairly optimized by the end. You can see that it's a constant red line now, whereas before there wasn't any red in this section. And we also got subtle improvements in all the domains, except, well, the first domain, this one, we got a significant improvement, reducing it from an 8% difference in flow rate and area to around 0.4. That's very good compared to before, at least. About a 7% improvement. So some of the other sections, like down here, and as well as here, it got slightly worse, but it's not very significant. It's about 1.5% at the most. If you go back to the default, you can see there's some red here, so it was a little bit more balanced around the circle before, but now it's not. But overall, it's a better design, like an even velocity. Since we can't change this section or this is about as good as it gets without changing the number of nodes that we have. So we kept the same amount of nodes. You could make it look more circular by adding some more if you wanted. So now I guess we'll just show how to adjust these nodes to the right positions to make the optimal die. We'll show the steps to do that. So go back to this. and we can edit the grid and then fill in those values.
All right, now that we've pick up where we left off, now that you've already seen all of the different profiles of the different transitions that we've gone through, we can go ahead and show you just real quick how to actually make those changes. So in the die cross sections, we're just going to go ahead and edit project 2, the BT2. Edit that. Go ahead and hit check. Alright, once we've got this already all popped up, we're going to go ahead and start trying to modify the locations of the nodes. So just go ahead and click on Move Node, and then we're just going to move our way down the side of our part, and basically it's going to end up being mirrored across this 45-degree angle, so it makes things a little bit easier to change as well. We're going to leave the points at the 6 millimeter mark where they are currently, but start moving the other ones. So move this one right here, hit the space bar to change it. We're gonna make this one be 1.2 by 6.8. And then to go ahead and do the mirror of that one, we're gonna do this one over here, and it'll be 6.8 by 1.2. All right, moving to the next one, will be this one. This one will be 2.6 by 6.9. Same thing over on the other side, just reversing those two, which is going to be 6.9 by 2.6. Alright, next one, this one's going to be 4.2 by 6.4. Do the same on the opposite one. 6.4 by 4.2. And then to move the last node, this one's going to be at 5.4 by 5.4. And then once we've got that created, hit escape to get out of moving nodes, and we just have to go ahead and generate that grid again. Just automatic and okay. So now that the grid's been generated, we can close out of it and save. Alright, and then give it a sec to pop back up, and we can go ahead and, since we've made those modifications to BT2, those we just want to make sure it has the same modifications on BT1, so we're just going to go ahead and delete the BT1 and make a copy of this and paste it back in. Rename it real quick. Just make that one be the BT1 again. And that's our other balance plate, so we just have to edit that and generate the grid on this one as well, making the Z be at -5 instead of -15. And it should have the exact same node location since we just copied it, and we just have to go ahead and automatically generate that grid again. The grid's all set, so we can close and save that one. And once this one's all saved, we should be ready to go ahead into the next tab and run it over in project data. We can edit our original one. And then just in case, to make sure that we have the correct things here, just gonna go ahead and replace them real quick to make sure that everything has matched and that there's no lag on those changes for any reason. We've got all those plugged into there, so we can go ahead and hit save and solve. Let that solve for a minute, and then we can go on to our solutions. So right now we can see that between each of these profiles, the pressure drop is decreasing as we get closer and closer to the die exit, which is what we would expect. And then if we just look at the cross section on this one, once this pops up, can now see that that's the cross section that we showed before, showing the fairly optimized flow pattern. And as mentioned before, we could go ahead and add in a couple more nodes along the outside to make this a smoother curve, but that won't affect the overall path flow too much. So this is a accurate representation of what we should have, and that'll be our final shape, and we should have a fully complete die. So make sure close and save all of that, and that is the end of the project.